So I'm going to start the recording here and just talk you through this. It says when a conditional statement and its converse are both true. Remember, a conditional statement is if P, then Q. So if I live in Houston, then I live in Texas. The converse, remember, is if Q, then P. If I live in Texas, then I live in Houston. Now that's not true. The converse isn't true in that case. But we talked yesterday about definitions. One example was about the perpendicular lines definition, which we'll look at. And remember that I said yesterday that a good definition is true forwards and backwards. So that means that the conditional is true and the converse is true. Now, if that's the case, then you can write a good definition. And not only that, you can change it. So we can always take statements that are have true conditionals and true converses and make them if and only if statements. And that's what this is saying. A biconditional statement is a statement that contains the phrase if and only if. Any definition can be written as a biconditional statement. Usually, in other books, they have you just write IFF for if and only if, so you don't have to write the entire thing out. The way that we denote that symbolically, and if you take a philosophy class and you like philosophy, you'll probably learn this as well. Yesterday we talked about how this applies to a lot of different coursework. They'll probably teach you that as well. So essentially, like I said, any statement that whose conditional is true and whose converse is true, you can turn into a biconditional and will therefore have be a good definition. So it says rewrite the definition of perpendicular lines as a single biconditional statement. If two lines intersect to form a right angle, then they are perpendicular lines. So you're going to take out the if and then, and you're going to put an if and only if in the middle of it. Two lines intersect to form a right angle if and only if they are perpendicular lines. That's how we would write that. So I'm going to take out that if and take out that then and rewrite it. Two lines intersect to form a right angle if and only if they are perpendicular. You can write perpendicular or perpendicular lines. So what I did was I looked at this. It's true as a conditional. It's true as a converse. Therefore, it can be written as a biconditional. And if I wanted you to identify the hypothesis, remember P is the hypothesis and Q is the conclusion of that if and only if statement, you would say the hypothesis is two lines intersect to form a right angle, and the conclusion is those lines are perpendicular lines. Does that make sense? Questions? Anyone confused? No. All right. So here we're looking at a truth table. Every truth table contains truth values, and those truth values are either true or false. What a truth table allows you to do is examine what your hypothesis is and what your conclusion is and say, if my hypothesis is true and my conclusion is false, can my statement still be true or will it be false? Does that make sense? So that's what you're going to be doing with a truth table. In other words, you're going to look and see what happens if both my hypothesis and my conclusion are true. Then the conditional statement that's formed must be true. If my hypothesis is true and my conclusion is false, then the conditional formed from the hypothesis and conclusion must be false. If my hypothesis is false, and this is a hard one, the third one is always the most difficult one. If my hypothesis is false, but my conclusion is true, the conditional is still true, and we'll talk about that. And if both of them are false, that means that the conditional is true. So we'll look at that. So those last two are a little bit more difficult to try and comprehend. We're going to look at a very simple conditional statement, an if-then statement. That's what a conditional statement is. If it is a holiday, then the store will be closed. Or if it is a holiday, the store will be closed. You have an implied then there. Now notice, on the last slide I said that that truth table is not going to work for a biconditional. If you look at this statement forwards and backwards, it may not necessarily be true. If we look at if it is a holiday, the store will be closed. If you say if the store is closed, it is a holiday, stores can be closed on days other than holidays. So that's not necessary, the converse is not necessarily true. Does that make sense? So we're going to take a look at this simple statement and its truth values. It's a holiday and the store is closed. So it makes sense that if it is a holiday, the store will be closed. So that first one checks out, yes? What happens if it's a holiday but the store is not closed? Well, they lied to us, right? They said, if we're looking at a policy, for example, if it is a holiday, the store will be closed. Well, the store happens to be open on a holiday. That means that they made a false statement. Does that make sense? So that conditional, if it is a holiday, then the store will be closed, would be false. So this is what we're looking at. If it is a holiday, comma, then the store will be closed. This is my hypothesis. This is my conclusion. So when that conclusion is false, but the hypothesis is true, the statement itself is a lie. False. Okay, the third one is the most difficult to kind of comprehend. Let's assume that the hypothesis is false. So it's not a holiday, but the store is closed. Would they be lying to you if that were the case? No. What other instances may a store be closed other than a holiday? Yeah, on a weekend, for example, right? This statement just says, if it's a holiday, the store will be closed, right? So that's okay if you're closed on a weekend. It's okay if you're closed because of construction. That does not mean that this statement is false. Does that make sense? Now, if it is not a holiday and the store is open, then of course this statement can still hold true, right? Does that make sense how I went through this truth table with that? Do you have any questions? That's how you have to think about it on these statements. You have to say, okay, is it possible? Can I think of a scenario in which my hypothesis is false, but my conclusion is true? In real life, that makes sense. And if you can, then the statement itself can still be true. And if that's the case, you write true. We are just looking to see if, wait a minute, this would be a straight up lie. And in that case, it would be the second instance where your hypothesis is true, it's a holiday, but your store's open. So here we're looking at a truth table for the following conditional. If P, then not Q. Not Q being the inverse. So the only thing that we're going to do is we're going to add an extra column for not Q. So, for example, if I had a statement, if you have a cat, then the cat is black. Not Q would be the cat is not black, right? And what you're looking at is if I have a cat, then the cat is not black, is what this means. And it follows the same pattern. If the premise or the hypothesis is true and the conclusion is false, then the entire statement is false. If the hypothesis is true and the conclusion is true, the entire statement is true. It follows this pattern every time. If the hypothesis is false and the conclusion is false, just like you can be open and it not be a holiday, then the statement is true. If the hypothesis is false and the conclusion is true, the entire statement can be true. And that goes back to when the store is closed on a weekend, for example. So it always follows this pattern. So as long as you know that, you really just have to memorize the pattern if you want to know this. The same is true for this one. Number 15 is a little bit easier. It's just saying write your traditional truth table. If they're both true, then the conclusion is true. If the hypothesis is true, anytime your conclusion is false, the statement must be false. You cannot have a false conclusion and have a true statement. You can have a false hypothesis and a true conclusion and still have a true statement. And all this is saying for number 15 is take your regular truth table and negate it. And it's just like the distributive property. Really what you're looking at is not P and not Q. So if they're both true, and if P not Q, then it's just going to be the opposite. It's going to be the opposite of what you see. If this is true, this is false. If this is false, this is true. If this is true, this is false, etc. And keep in mind, another hint for number 14 would be, if you're saying Q is true, not Q has to be false. Q and not Q cannot be true both at the same time. That's saying the cat is black and the cat is not black at the same time. You can't have a cat that is both black and not black. Well, but it's still black. It just has white with it. Okay. All right. Did I just blow your minds, or do you kind of get it? Sort of? Yes? No? How many of you, this is kind of interesting, I sort of get this. Anyone? Okay. How many of you are like, whoa, Miss Wynn, this is way over my head? Anyone? Okay. And how many of you are okay with the last one, maybe not okay with 14 and 15? Anyone? All right. Are there any questions that you have on this that I can answer to help clarify before I move on?